Welcome to the session titled Robotics and Autonomous Systems for Aided Intelligence. My name is Anila Medi. I'm an application engineer at CES, the authorized reseller of MathWorks in the Middle East. Today, we will discuss the exciting topic of robotics and autonomous systems for aerial intelligence. Here is the agenda of our webinar. In this presentation, I will begin with an introduction to robotics and autonomous systems for aided intelligence and the role of model-based system engineering in enabling advanced aerial capabilities. I will then discuss MathWorks solutions that support design, simulation, and deployment of autonomous systems through model-based development approach. Following this, I will provide an overview of the MATLAB and Simulink ecosystem for aerial intelligence, highlighting how these platforms integrate control perception and mission logic within a unified environment. In the next section, I will outline why MATLAB and Simulink are ideal for aerial intelligence applications, focusing on their strengths in the algorithm development, integration, and code generation for real-time deployment. I will then present representative application examples that demonstrate the use of MathWorks tools across surveillance, environmental monitoring, and precision agriculture. Finally, I will conclude by sharing key resources to support the adoption and advancement of aerial intelligence development using MATLAB and Simulink. Let's get started. Robotics and autonomous systems for aerial intelligence. So what does it mean? It's mainly the use of unmanned and intelligent aerial platforms like drones or UAVs equipped with AI-driven technologies to collect, process, and analyze aerial data for various applications. It combines robotics, sensing, and AI to perceive, plan, and act autonomously in complex environments. So basically, the aerial intelligence harness the power of drones, advanced sensors, AI analytics, and 3D reconstruction to enable fast and confident decision making. So the core of these kind of systems are nothing but the robotics and autonomous systems. And this is what makes aerial intelligence possible. They transform the drones from being remotely piloted devices into intelligent mission autonomous systems. The physical platforms, which are nothing but the robotic systems, these are capable of sensing, decision making, and acting in the environment. And the autonomous part, these are the systems capable of operating independently or with minimal human intervention using onboard intelligence. And these systems usually include key components like perception, for example, different sensors or cameras or lidars or radars for situational awareness. And another component is decision making. This includes algorithm for path planning, obstacle avoidance, and mission logic. It also contains control and actuation components as well as the communication parts. Let's have a look at the applications of the robotics and autonomous systems for aerial intelligence. If you consider agriculture and environment, this type of systems can be used for crop health monitoring, precision spraying, wildlife and forest tracking. And if we consider the infrastructure and maintenance part, it can be used for power line and pipeline inspection, bridge and tower assessment, then construction progress tracking, etc. And when it comes to the security and defense and law enforcement, it can be used for ISR. ISR stands for intelligence, surveillance, and reconnaissance. And similarly, there are a lot of applications for this kind of robotic and autonomous systems for aerial intelligence. I have listed a few here in the slide. Here is some examples based on US Defense Department's classification on the levels of autonomy. So there are mainly three categories. So the level 0 means it's purely manual or it's remote controlled, and level 1 means it's simple automation, and level 2 means automated task and functions. So going forward, it has levels up to 10, and the level 10 means it's autonomous conglomerate. And I have listed some examples for each category also. Like if it is Predator by General Atomics is an example for level 0, and Global Hawk by Northrop Grumman is an example for level 3. And for the third level 7, we have ARSA. It's nothing but urban reconnaissance through supervised autonomy. It's a defense program, mainly DARPA program, to enable improved techniques for rapidly discriminating hostile intent and filtering out threats in complex urban environments. So these three groups can be roughly summarized by the terms unmanned vehicle, autonomous system. Where would you say that your program or the team is focused in general? Are you developing any unmanned aerial vehicle, or unmanned ground vehicle, or unmanned surface vehicle, or unmanned underwater vehicles, etc.? So you can comment it out, comment it in the chat if you're a part of such system development. One framework some folks use to think about the technology landscape for such autonomous systems or system of systems is the modeling and simulation pyramid, which is smaller at the top to denote the increased aggregation and scope, and larger towards the bottom for the number of components that might be modeled with increased fidelity. So at the bottom, you can see it starts with a simple system like the engineering system. It may have many, may have a platform and many subsystems. And going upwards, there comes the engagement or the unit. It may have one versus one, or one versus few, or one versus many such systems. And then it goes up to the campaign level. Another way of thinking about that landscape is by using the mission engineering perspective. At the component level, the engineers and scientists might be developing something like the sections of a hull of a modular underwater vehicle, and then comes the system level. So here the system engineers and program managers might be interested in system level performance of the vehicle in terms of its specifications measured against a set of requirements. This could be physical specification or performance specification. And then next is the system of systems. Uh, this can be like it's a level of machine engineering, and this is what you have seen in the previous slide, like the DARPA has been promoting in terms of a mosaic warfare concept. So how does this fit into a total package, and what tiles are needed to connect it into a bigger picture? And then there is a mission level, which is ultimately the most important driving force in this picture. The digital engineering vision is needed to accomplish all these things. And if you want to answer all these, the mission engineering view and different levels, and as shown in this diagram, we need to have a reasonable degree of confidence with the models at the foundation level, which is built using digital engineering. And I think MathWorks can help connect the stakeholders across all levels here. Model-based system engineering is a key enabler for mission engineering, which focuses on achieving mission-level outcomes rather than just developing individual systems. In mission engineering, where multiple systems like UAV, sensors, the communication links, ground control must work together towards a common objective. And MBSE, or the model-based system engineering, ensures interoperability and coherence across the system of systems. It also supports in digital mission threads like linking models across different life cycle stages from concept of operations to verification and validation. Let's see what exactly the MBSE or the model-based system engineering means. Here is the definition as per the in-course SE vision. Uh, it's a formalized application of modeling to support system requirements, design, analysis, verification, and validation activities, beginning in the conceptual design phase and continuing throughout the later life cycle phases. So what does that mean? The formalized application, so and so things. Let's split this definition. Let's consider one by one. So model-based system engineering is a formalized application of modeling. What does it mean is it is well structured, it is documented, it is practiced, and it is well supported. And then the next part is the application of modeling. So these models can be a physical model of your electrical or mechanical system, or a combination of both, or it can be a behavior modeling, or it can be a functional model. Okay. So in any ways, modeling is a core practice of model-based system engineering. And then comes the support the system requirements, design, analysis, verification, and validation activities. These are some of the common or the practical steps in any product design. So when you are adapting model-based system engineering for your product development, you should be using modeling to support all these activities. It starts from the conceptual design phase and it continues throughout the development and later life cycle process. Almost every engineer is involved in some degree or form, and it covers many types of products. It can be hardware, or it can be software, or it can be a service oriented activity. We have just seen the definition of model-based system engineering, and the question is how to use MBSE in a product development. There are several system engineering approaches that can be used to support MBSE. For example, agile system of engineering, system of system engineering, modular open system approach, or V model. What you're seeing on the slide is the V model. It's presented in a detailed way. So if you look at this V cycle, it starts from the requirement phase on the left side. It then goes through the system requirement analysis, system design, and then the requirement analysis. Then we further divide it into electrical or mechanical parts, and then the electrical parts may have software as well as the hardware things. Then we go to the component level. It is followed by production and implementation. And for each of these activities on the left side, there is an associated testing that you can see on the right side. So at the component level, you should be doing the unit testing, and once your components are integrated, you have to do the integration testing, and once it reaches the system level integration level, you have to perform the system integration testing as well. And here you can see a term called model-based design. Okay, so it's nothing but the systematic use of models throughout the development process that improves how you deliver complex systems. It mainly has two parts: modeling and automation. Modeling means modeling with simulation and analysis, where you can try out new ideas and it gives you fast and repeatable tests. And the second part is nothing but automation. So it involves coding and verification. This component will help you to take out the manual steps, and it will help you to reduce human errors. Let's see. And MathWorks is a one-stop shop for model-based system engineering. We have the solutions supporting each of these activities that you have seen in the V cycle. Okay, so we provide solution for architecture and design analysis, control algorithm development, rapid control prototyping, report generation, and if you have any safety standards to meet like ISO 26262 or DO 178C, we have the solution for that. And sometimes your project may include physical modeling of the electrical mechanical systems, so we have the solution for that. And it is followed by the code generation for the the controllers that you are using. So we have solutions for that as well. And for the testing, which is on the right side, it can be model in the loop or software in the loop or processor in the loop or even hardware in the loop. And finally, the system integration testing. So MathWorks provide a solution for all these. Let's see an example how you can implement this V-cycle in system development. Okay, we are going to use the delivery with a drone as an example to think about what does it mean. Okay. So first, we have some stakeholders. They have some needs about the drone delivery method. Based on that, we derive some requirement for our system about the weight, capacity, range, and all. Okay, and then we create the subsystem architecture and the system architecture, the connection of those. For example, the path planning, battery management, propulsion, flight control, etc. And then we go to the component level design or the battery, the propeller, and the control algorithm. And then the next step would be the implementation of those and verification of that in real hardware. And then you have to create this in a physical world if you're designing a hardware, and then create those components together to create subsystems that you have and verify those designs. And at the end, you combine all of those and create your system and verify that and then operate and maintain your product. In all these steps, you have to do some validation with the models, requirements, and simulations that you have on the left side of your diagram. As you see on the top, we are working on the system level, and at the bottom, we are working on the component level. It would be more cost effective to catch any issue in the earliest stage of the product design, pinpoint and resolve them using MBSE practices. What you have seen is a drone being used for delivery application. So we have the solutions for helping you to accomplish all the activities mentioned in this. Now let's see how MathWorks help in the development of autonomous system development. We'll start with the common challenges and then see the activities included in addressing each of these challenges. Okay, so coming to the so this lists the challenges in different phases of that product development, autonomous system development. Maybe we may be starting with the system definition. So you may have some challenges with the documentation of your requirements as well as managing the traceability from requirements to code. And coming to the platform side, it may be about how do you model the physical interaction and the system dynamics. And on the autonomy or the algorithm design, the challenge may be about designing fusion algorithms that incorporate data from various sensors. Sometimes it's about designing path planners for different optimization goals, or sometimes it's about how to visualize and analyze data from different robots. The challenges can be related to verification and validation also, and sometimes it's about how to evaluate your algorithms in a photorealistic simulations. And there can be challenges when you try to connect to your platform or to the robot. Okay, so how to design data acquisition system via robotic operating system, etc. And finally, when it comes to the deployment to the hardware, if you're using manual codes, and then and finding an error in the later stage or in the hardware part, it will be very difficult and it may cost you a lot. So we will recommend you to do simulation before, and will recommend you to do the simulation and use automatic code generation capabilities, so it can save your time and cost. Here is an example of different activities which are involved in autonomous flight development or a UAV development. So for the system definition, platform design, autonomy, verification, validation, 3D design scenario, connection to robot, implementation to hardware, these are some of the commonly used activities, and we have the solutions addressing all these things. And already there was a webinar which is conducted in last year. It shows in detail about how to use model-based system engineering approach for this kind of autonomous system development. Okay, the recording of this webinar is available in CES YouTube channel. Please have a look, and if you are interested to know more, please make sure please feel free to reach out to us. The webinar title is Model-Based MBSE for Robotics and Autonomous Systems. Next is about MATLAB and Simulink Ecosystem for Aerial Intelligence. So in this part, okay, let's start with some of the key components of the aerial intelligence system. As you can see, any aerial intelligence system may have an aerial platform. It may have different sensor payloads based on the application, and it includes data processing and analytics, autonomy and control systems, communication and data links, ground control station, cyber security, and data management. So most of these parts are covered in our previous webinars, like I just mentioned. So please have a look if you are interested. And in today's webinar, I will mainly be focusing only on the different types of sensors and how can you process the data from such sensors, and then how to develop autonomy algorithm from that. Here I have listed some of the commonly used sensors in aerial intelligence applications. It can be camera, or it can be lidar or radar, or even hyperspectral images. So if it is if your sensor is a camera, then probably you need to read and stream it. And then if it is a lidar, then you may need to read or stream it. And when it comes to radar, it's probably about reading the data from the radar. And similarly about the hyperspectral images. So I have listed MathWorks solutions for each of these things. For example, if your sensor is a camera, then we have the image acquisition toolbox. It helps you to connect your cameras with the MATLAB and Simulink. It also provides functions and blocks for it also includes a MATLAB app that lets you to interactively detect and configure the camera hardware properties. And on the if your sensor is a lidar, we have the lidar toolbox that provides algorithms, functions, and apps for designing, analyzing, and testing lidar processing systems. It helps you to perform object detection and tracking, semantic segmentation, shape fitting, lidar registration, and obstacle detection, etc. If your sensor is a radar, okay, probably you need to know the range, Doppler, and angle information. So we have the radar toolbox. It provides algorithms and apps for designing, simulating, analyzing, and testing monostatic, bistatic, and multifunction radar systems. Another toolbox that is very useful in this category is phased array system toolbox. It provides you tools for designing and simulating phased array and beamforming systems for wireless communication, radar or sonar or acoustic applications. Another useful product if you are handling hyperspectral images is the hyperspectral image support package. It's a part of the image processing toolbox. It provides you, it can help you with the importing, visualizing, processing, analyzing, and exporting of hyperspectral data. When it comes to the data processing and algorithm development part, okay, so for the image processing, like I mentioned, we have the image processing toolbox. It provides you a set of reference as well as the standard algorithms and workflow, and also apps for image processing, analysis, visualization, and algorithm development. And on the other hand, we have the computer vision toolbox. This also provides you algorithm and apps for computer vision systems. It helps you to perform visual inspection, object detection and segmentation, camera calibration, visual slam, etc. For the radar, if your sensor is lidar, then as I mentioned earlier, it comes with the different functions and apps that helps you with the point cloud processing and object detection, semantic segmentation, etc. Radar toolbox I have already mentioned. The another toolbox which is listed here is the sensor fusion and tracking toolbox. So this will help you to design, simulate, and test multi-sensor tracking and positioning system. This is particularly useful if you want to do some situational awareness and localization, etc. And then there comes our hyperspectral image processing. So it's again with the hyperspectral image support package. So it helps in the visualization, analysis, filtering, data correction, dimensionality reduction, etc. And this also comes with an app like a hyperspectral viewer app. It helps you to read hyperspectral and multispectral data and display metadata, etc. So further for the algorithm development, we provide AI-based algorithms and models. So it's anyways important to have direct access to many algorithms used for classification, prediction, from regression to deep networks and clustering. So and there is a our toolboxes provide some variety of pre-built models developed by the broader community that you want to use, often as a starting point or for comparison purposes. While the algorithms and pre-built models are a good start, it's not enough. We also provide apps for modeling as well as data preparation. For the deep learning in particular, we ship pre-built apps that help you to automate the training step and provide visualization for understanding and editing deep neural networks. And there are apps like a classification learner and a regression learner. It helps you to automate those steps as well. And then there is the experiment manager app. It will help you to create deep learning experiment to train your networks under various initial conditions and compare the results. And examples are the way engineers learn how to use the algorithms and find best approach for their specific problem. We provide hundreds of examples for building AI models in a wide range of domains. The next topic is about why should you use MATLAB and Simulink for aerial intelligence application, especially over other softwares. Here is the reasons why you should use MATLAB and Simulink for aerial intelligence applications. We support an end-to-end workflow. It's starting from the conceptual phase to simulation, and then finally to the deployment. We have the solutions. So if your platform is for the aerial platform development, we have accurate UAV and sensory modeling options. We also provide built-in AI and machine learning integration, and there are solutions for real-time testing, especially if it is rapid control prototyping or hardware in the loop. We can cover that, and then we also provide solutions for advanced data fusion visualization. And finally, MATLAB and Simulink is certified and reliable and scalable environment. So here, I've just mentioned about different solutions. Let me show you an example of LiDAR data, aerial LiDAR data segmentation using AI and toolboxes. First, I will start with a simplified view of any AI-driven system design workflow. So it has mainly 4 stages: data preparation, AI modeling, simulation and test, and deployment. In this demo, we are applying a semantic segmentation network for a large point cloud using block processing. Semantic segmentation of point cloud is a process of classifying each point in the point cloud based on the object that is present at that position. Here for this demo, we are using a state-of-the-art neural network, PointNet++, which can segment point cloud into different classes like vegetation, buildings, road, etc. This PointNet++ is a hierarchical neural network architecture designed for processing 3D point clouds, building on original. It was built on the predecessor named PointNet. This neural network is particularly useful if your LiDAR data is unorganized. Okay, and the first step is the data preparation. So here you'll create the block and build the point cloud, and then pre-process this point cloud to prepare it for applying the AI model. In the second step of AI modeling, you have to define a PointNet++ network to segment the point cloud. And in the third step, we will see how we can test our model on a simulated data. And then finally, we will deploy the algorithm on a target hardware. MATLAB gives you the flexibility. The first step is the data processing. Sorry, data preparation. And MATLAB gives you the flexibility to read data from popular files to file formats such as LAS, LAZ, PZD, PCAP, etc. You can also stream live LiDAR data from Oster or Velodyne sensors. In addition to this, you can read point cloud from ROS bags also. So once we have loaded the point cloud data, we can use the LiDAR Viewer app to visualize, analyze, and edit the point cloud data. We can import point cloud in different file formats like LAS or LAZ. We can toggle between different types of visualization like red to blue and Farula. We can adjust the size of the points, zoom in or zoom out, and pan. Then we can select different views, including custom views and many more. The key feature of this app is that it allows us to apply basic pre-processing algorithms such as denoising, downsampling, and ground removal. Denoising and ground removal on the point cloud interactively. So in the video, it shows the different pre-processing steps. Also, in this video will show how to remove the ground and to crop the point cloud to an ROI. Once we are done with the pre-processing, we can export the pre-processing functions as well as the processed point cloud into MATLAB workspace. Now we have read the point cloud, pre-processed it, and visualized it using the LiDAR Viewer app. You can also pre-process the point cloud data using the command line functions. So you can find a variety of point cloud pre-processing functions in our documentation page. In our workflow, we are implementing downsampling and normalizing functions. Here is an example. We can use the PC downsample function on the point cloud without compromising its structures. We can also do the normalization on the point cloud based on the XYZ limit and range with a few lines of code, as you can see here. The next step is about the segmentation. So we will segment the point cloud. While our focus is on deep learning based segmentation, I will give you a brief overview on other segmentation techniques as well. Different methods used for segmenting LiDAR data include classification using feature extraction, and semantic segmentation. For this example, we'll be mainly using semantic segmentation. If you are using clustering, yeah, here is the information. If you are using clustering, in MATLAB, you can use PCSegDist function or segment the LiDAR function for clustering. PCSegDist function segments the point clouds into clusters based on the Euclidean distance between them, and we will give a minimum threshold value. Sorry, the video is not playing. Okay. PCSegDist function. So you have to, it uses the Euclidean distance to segmentation. Then we will give a minimum threshold value between the points from different clusters and then apply the function. While pieces of this function can be used both on organized and unorganized point clouds, segment LiDAR function is designed to cluster organize the point clouds, resulting in faster execution. Next method is classification using feature extraction. Here, the features like normals or the curvatures of the points on the point cloud data. So this uses the fact that the buildings are more planar than the vegetation, and the vegetation points are more scattered, which then result in a higher change in value of curvatures compared to the buildings. So using this difference, we will segment the point load into buildings and vegetations. Last method for segmentation is it uses the deep learning models. So here we will be using the state-of-the-art PointNet++ to segment the point cloud. It's as I mentioned earlier, it's a neural network used for semantic segmentation of LiDAR point cloud. It classifies each point in the point cloud based on different classes like cars, trucks, drones, or vegetation. The network contains an encoder with a set of abstraction modules and a decoder with the feature propagation modules. The network tries to find local features and then group them into larger units to find higher levels of features from LiDAR point clouds. There's a detailed documentation available for helping you to getting started with the PointNet++ network in our website. If we zoom into our output, we can see that the output resembles the ground truth data. Now let's see how we got this output using MATLAB's block preprocessing workflow. As a first step, we will define the block size and create the block point cloud object and the block point cloud data store. This data store will help us to manage the point clouds and avoid out of memory issues. We will then define few parameters that we would need to apply the network, like class names and the number of points in each block. After that, we load the pre-trained point net++ network. Now let's go on and read the individual block from the data using the read function, and then we will extract the labels from it. We will now process the point cloud block. As I mentioned before, we mainly apply two pre-processing steps here. First one is downsampling, and second one is normalizing. After that, we will apply the network on the block point cloud using semantic seg function. Finally, we will assemble the point cloud block, and then we will stitch the whole blocks together. Here is our final output. You can see that we have segmented the input point cloud into different classes like buildings, trees, and ground. Now, if you want to test your network before applying it into a real-world system, you can use simulation environment available in Simulink. So here, sorry. Okay, so here I'm simulating a city scenario with the UAV flying based on different trajectory. So in this model, you can see a LiDAR sensor is mounted, and then we have defined a few sensor parameters based on my need. Now, it's not playing, right? Okay, something is wrong. Okay, so this is actually a screenshot of the model which is being used. Now we can run this model and collect the point cloud data, and then apply the AI model to test the model on the data. Last step in the design in AI-driven system design for segmentation of aerial LiDAR data is about the deployment. So we have segmented the point cloud. Now let's move on to the final step, that's the deployment. So from MATLAB, you can generate C++ code as well as the CUDA code for deep learning. You can use the MATLAB coder for C++ code generation. First, you have to specify the MATLAB function name. This example shows the C code generation. Here there is an option for C++ as well. So for any code generation, first you have to mention the function name and then the input attributes. After that, you can generate the code. Then this code provides a report which you can use it to trace it back to the corresponding MATLAB code. You can generate GPU code using the GPU coder. Okay, so the GPU coder from MathWorks provides, it helps you to generate optimized CUDA code from MATLAB code and Simulink models. So here I have shown you the screenshot of an example. So this example in the LiDAR toolbox documentation, it explains the entire process of GPU code generation that you will need. And for this one, you need to have a CUDA enabled GPU as well as the compatible driver. It's not only GPU code that you can generate. We have unique code generation framework that allows models to be developed in MATLAB or Simulink, and it can be deployed anywhere. So, sorry. You can generate C++, CUDA, Verilog, VHDL, or PLC code using the coders from MathWorks. So with this, I'm wrapping up the workflow for aerial LiDAR processing. So we have the solutions to read, stream, and write the LiDAR data, and we have functions that supports in the block processing, and there is a complete AI workflow with the pre-trained models, training, evaluation, and validation, and we have the apps that help you in labeling the data. And for the deployment, we have a range of coders. Next one in next topic in the next topic is about Few examples related to aerial intelligence applications development with MATLAB and Simulink. So here is the first one is about detecting risk trees near the power lines. So this example shows how to detect the trees that could fall on power lines and cause outages and interruptions. So the risk trees are detected from point clouds collected from aerial lidar scanning. The lidar the LiDAR data can provide you information on vertical structure of the trees, and it can also penetrate foliage to provide the elevation information on the ground. So if you're developing such kind of an application, it includes mainly uh, like few steps. That is what I have listed on the slide. First, you have to load the point cloud data, and then you have to extract the power lines from this data, then segment the individual trees, and you have to detect the risk trees, and you can visualize the risk trees on the map. Another example is about simulating the safe landing of UAV in unexplored environment. To safely operate in an unexplored environment, a UAV needs to have an autonomous safe landing capability. If the UAV detects a critical anomaly such as abnormalities in the battery or a navigation system, the UAV must be able to scan the environment, determine a safe landing zone, and safely land without hitting any obstacle. To scan the environment, the UAV uses LiDAR sensor data to create a map of the unexplored environment and then determine the safe landing area. Here for this example, it uses the toolboxes like a Simulink LiDAR toolbox, state flow, Simulink 3D animation, and UAV toolbox. This is another example. It uses UAV data, and this is one of our customer story from Intel in Air. It's a US-based precision agriculture company. It provides it specializes in aerial imagery analytics. Uh, and they leverage a combination of visible, near infrared, and thermal cameras. They capture images throughout the growing season, giving the farmers a snapshot at a given time, gathering trend data for long-term planning, and alerting the farmers about the problems so they know where to take the action. And finally, resources to start your transformation journey. So I have mentioned about few toolboxes throughout my presentation. So here is some snapshots of the product page. So we have the computer vision toolbox if you are developing some computer vision applications, and then if your application is about if your application needs situational awareness as well as localization, sensor fusion and tracking toolbox can help in that. And as I mentioned earlier, if your aerial intelligence application uses a lidar, then we have the lidar toolbox to support you in that. And if your application involves any sort of radar like monostatic, bistatic, or multifunction radar system, we have the radar toolbox as well as the phase array toolboxes to support you in this. And here comes the image acquisition toolbox as well as some information about the hyperspectral image support package. And here is a few more examples like mapping the flood areas using the Sentinel synthetic aperture radar data. And this is the second one is about object detection using the large satellite imagery using deep learning. Here mainly we are identifying the airplanes which are parked. Here is some examples related to the hyperspectral image analysis. And to help you with the transformation with the right supports, MathWorks provide you trials and evaluation, consulting services, training services, and technical support. CES will also support in the same in these activities. So if you have any um, uh, if you need any support of this kind, you please feel to reach out to us. Thank you.